All right, so let's talk about types of changes. So there's two types of changes, physical and chemical. Physical changes are when the identity of the substance remains unchanged. I've never been a fan of this stuff, honestly. So just bear with me a little bit, and I probably won't stress this on any test or anything. So one thing, physical changes, one way to determine a physical versus a chemical change, physical changes are often reversible. It's not always true. When you cut a stick, both parts of the stick are still stick. So that's not reversible. I guess you could glue it back together, but then you're putting glue in there and whatnot. But when I say reversible, I mean like melting. If you melt something, you can freeze it back to the way it was. If you boil something, you can cool it down back to a liquid. So anytime you break something or grind it up, cut it up, any of the phase changes, like I was just talking about, bending something, ripping something, those are considered physical changes. Chemical changes, what's more important than their chemical changes is how to identify them. So you make new substances out of other things, burning, rusting, molding, rotting, growing. We also call this, and that's the one that upsets me, growing is considered a chemical change. So grass is still grass as it grows, but that's considered a chemical change, not a physical change. And that's where this becomes a little more philosophy, and I don't like getting into it. So, but you do need to know when a chemical reaction takes place. And the way to know that is through these four things. When you make bubbles or a gas formed, that is a sign that a chemical change took place, that there's a chemical reaction. When you form the solid, so look here, we got a clear liquid and we got it going into another clear liquid. So here's a clear liquid and here's a clear liquid, and this solid is formed, and that solid is called precipitate. And a precipitate is a sign that a chemical reaction has taken place. Anytime energy is released as heat or light, that's a good sign of energy, that a chemical reaction took place. And I don't love that this color is so bland, but anytime there is a color change or a change in smell, that's an indication that there's been a chemical change. All right, so the phases of matter you should have learned at some point. If not, here they are. Solid. Solid will have particles close together, definite shape, definite volume, right? The size of my cell phone or my eyeglasses doesn't change whether I put it on one table or a different table. It has a definite shape and takes up a definite amount of space, whereas liquid can change its shape, right? You pour it out from a bottle onto the floor. It's no longer the shape of the bottle. It's sort of the shape of a puddle. And likewise, you can pour it into different shaped containers, and the liquids will just take the shape of their containers. So liquid's definite volume, but doesn't have a definite shape. The molecules are not so close together, or the particles. And then gas is neither definite volume nor definite shape. It takes the shape of the container. And we will do a FET with this, which I really enjoy, an interactive, either in class or maybe from home, one or the other. Okay. So what do you imagine happens with mass? So as the mass of something gets bigger, right, it's harder to move around. And because of that, things that have more mass do tend to be solids more than gases. So if we go back to our periodic table, a lot of the gases don't weigh a lot, and a lot of solids weigh a significant amount. But we'll get into that some more later. All right, so temperature, we typically measure temperature in Celsius when we're in science classes. And we convert it to what we call the Kelvin scale. The Kelvin scale is based on the idea that at 0 Kelvin, there's no particle motion. So what temperature should be measuring is the motion of particles, and it makes sense that at 0 temperature, there would be no motion. So something gets so cold where all motion stops. And so that's why we use this Kelvin scale. And again, when we play with that FET, you will be able to experience that. So at absolute 0 Kelvin or minus 273 Celsius, there is no motion of particles. Any other temperature will have a little bit of motion, whether it's a solid, liquid, or gas would be regardless. It would still have temperature. So the way you get Kelvin is you take whatever the temperature is in degrees Celsius and you add 273. Examples: if it was 100 degrees Celsius, what would that be in Kelvin? Well, you just need to add 273, and you would have 373 Kelvin is what that is. And if you had minus 23 degrees Celsius, you would add 273, and then you would get that to be 250 Kelvin is what that temperature would be in Kelvin. So minus 23 degrees Celsius seems pretty cold to us, but there's still motion, right? It's still significantly above 0 Kelvin. So therefore, there's still motion of particles, even if they're at minus 23 degrees Celsius. All right, these changes in states you should know. Solid turning into a liquid is melting. Liquid turning back to a solid would therefore be freezing. Liquid turning to the gas at any temperature, not at an elevated temperature, we call that evaporation. But if it happens at what we call the boiling point, that is boiling. That's a subtle difference. I'm not going to play games. I'm not trying to trick you on these things. I hope it'll be clear on whatever sort of testing situation we have. Gas turning to a liquid is condensation. So that's what happens on the mirror when someone's in the shower and all that hot water turns into a gas and then recondenses on the mirror. That's condensation. These last two deal with sort of dry ice. Basically, if you turn a solid right to a gas, if you've ever seen dry ice, that's sublimation. And if you turn a gas right back to a solid without going through a liquid, we call that deposition. Anyway, all right. So now we're going to talk a little bit about density. Density is another property of matter, and it's the mass divided by the volume. And we'll do a little FET about this as well, hopefully. Mass is measured in either grams or kilograms, ideally grams. Volume is measured in either milliliters, liters, or centimeters cubed. And so basically what you're going to do is take the mass of something and divide it by the volume, and you'll get some number, and that number represents the density. And we will, as I say, definitely interact with this some on a FET through class or as a homework situation. But one way to remember this formula, that mass over volume, is that density is equal to mass over volume. And when you put the M of a mass divided by the V of volume, it kind of looks like a heart. A lot of people use this pyramid where mass divided by volume equals density. Density, so density equals mass over volume. Volume equals mass over density. And mass equals density times volume. So this would be times, and these would be divided. So just another thing we'll go over in class some. So here are some examples. If you have 35 grams of lead, has a density of 14 grams per centimeters cubed, how much volume does that lead take up? Well, what you know then is that 14 grams over centimeters cubed equals, this is in grams, and this is telling you put it on top, 35.0 grams. And you want to know the volume, right? How much volume? How much? That's your x. So this is your question mark, right? So 14 over 1 equals 35 over x. You can cross multiply at that point, or however you like to do that. So 14x equals 35, and x is equal to, hold on a second, grab a calculator. So x is equal to 35 divided by 14, 2.5. And the units of that, because this was centimeters cubed, would be centimeters cubed. Okay, using this thing, we are trying to find this, so we should just take the mass and divide by the density. So when you think about what we did, we took the mass, which was given as 35 grams, and divided it by the density, which was 14, right? And that's how we got the 2.5. Okay, so here's gold's density. A cube of gold measures 2 centimeters on each edge. What is the volume of the cube? Well, if a cube is made of 2 centimeters on each edge, so each edge is 2 centimeters, the volume would be that times that times that. So 2 centimeters times 2 times 2, which becomes 8 centimeters cubed. All right, so the volume of the cube is 8 centimeters cubed. What is the mass of the cube? So if we're looking for the mass, that's equal to, the mass is equal to the density times the volume. Density times volume. So the density is given as 19.3 grams over centimeters cubed, and we're going to multiply that by 8 centimeters cubed, and then look here, the centimeters cubes cancel, so you're just multiplying 19.3 by 8, and the grams is what stays standing, and that's why that is the mass. And how come this thing works? So it's 154 grams, and if you put 154.4, that would be fine as well. All right, here's some densities of common substances. As we can see, the sort of barometer of densities not actually given here is water. Water has a density of 1. So water has a density of 1.0 grams per centimeter cubed. So these things tend to float in water because they have less than the density of water. These things tend to sink in water, if not dissolve, because this one dissolves. But that's why they sink in water, is because they have a higher density. And here you have some, oh, there it is, water. Water is 1, essentially. Gasoline floats on water because it has a lower density. Alcohol would mix with water. Kerosene would float on water. Turpentine would float on water. Okay, seawater, milk basically is the same as water. Mercury would sink to the bottom of water. All right. If you're constructing a line graph, you should always have a title as y versus x. I never knew that until I started teaching high school. It's not that big a deal for this class, but just if you go on to some science class, someone might really think that's important. So anytime you're going to measure something with a graph, the title of the graph should be whatever the y-axis is. So whatever this axis is, right? Versus whatever this axis is. Okay, choose the correct scale of increment, right? And we're basically going to do this in class where you have volume going from 0 to 50, and the biggest number here is 60. So you got to make sure when you're doing your graph that you have room for enough little tick marks to get to 60 on your mass part, and that your volume part can get up to 50. So this is where we're going to do that. So the volume is going to be the x, and the mass is going to be the y. So if our title of this would be mass versus volume. So this would be mass versus volume would be the title. And then we just got to make sure that we have enough. So on the bottom here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 hash marks. If we make every 2 10, or every 1 5, we would have room for 60. So that's going to work. So if this is 0, then this would be 10, 20, 30, 40, 50, 60. So that would fit on our graph, right? We didn't use too little room by making everything 1, because then we'd only be using this much of the graph paper, and we didn't use more room than we had by making every one of these hash marks equal to like 2 milliliters, because then 60 would be off the chart. So then going up with mass has to fit to 50, and we have here 1, 2, 3, 4, 5. So if we were going to make every one 10, that's where we'd go. 6, 7, 8, 9, 10. If we make everything equal to 5 grams, we can get up there. So that works best here. So 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. And then you just graph different things, right? Object A, B, and C, and we'll do that in class. And you put them on there, and you can determine the densities based on where those things end up. So I'll allow you to do that and check later with me. And I think that's where we're going to stop here.